Good morning, students. In continuation to the yesterday's class on measure theory, so today let us prove one or two important results. First one, say suppose f is a function from x to y where x and y are subsets of real numbers. Now, if f is continuous and b contained in y is a Borel set, then its image f inverse of b is a measurable set. Okay, understand this? So, if f is a function from x to y where x and y are subsets of real numbers, if f is continuous and b is a Borel set in y, then f inverse of b is a measurable set in x. Okay, for this, let G be the set containing set of all A such that f inverse of A is measurable. G is containing set of all A sets A such that f inverse of A is measurable. First, we show that this set G is a sigma algebra. Sigma algebra means we need to prove two conditions. Say, suppose E is contained in G. What you have to show? E complement is also contained in G. For this, now E is contained in G means by definition of a G, what will happen? F inverse of E is measurable. F inverse of E is measurable. Since complement of a measurable set is measurable, okay, we have f inverse of E complement is measurable. But f inverse of E complement is f inverse of E complement. Okay, you know this. Thus, f inverse of E complement is measurable. F inverse of E complement is measurable means what? E complement belongs to G. E complement belongs to G means if E belongs to G, E complement belongs to G. So, first condition of a sigma algebra we've been proved. So, let us take up the second one. Let EI be a countable collection of members of G. Let EI, I is equal to 1 to infinity, belongs to G. Then by definition, f inverse of EI is measurable for each I, right? Now, since the countable union of measurable sets is measurable, we have union I is equal to 1 to infinity, f inverse of EI is measurable because these are measurable sets means countable union of measurable sets is measurable. But union I is equal to 1 to infinity, f inverse of EI can be written as f inverse of union I is equal to 1 to infinity EI. Thus, f inverse, this is measurable means, thus f inverse union I is equal to 1 to infinity EI is measurable. This is measurable means by definition of G, union I is equal to 1 to infinity EI is an element of G. Is an element of G. Thus, G is a sigma algebra. Now, given the condition f, in the given condition as f is continuous. F is continuous means f inverse of O is open for a very open set O in Y, right? This is by definition of a continuous function. Now, since open sets are measurable, f inverse of O is measurable for each open set O contained in Y. For each open set O contained in Y. Thus, all open sets are in G. Thus, all open sets are in G. Hence, G is a sigma algebra that we have proved containing all open sets. Containing all open sets. But we know that Borel sigma algebra is the smallest sigma. Borel sigma algebra B is the smallest sigma algebra containing all open sets. Okay. Borel sigma algebra is the smallest sigma algebra containing all open sets means what? This Borel sigma algebra B is contained in G. B is contained in G. The elements of Borel sigma algebra are called Borel set. Thus, if B is a Borel set means B is an element of B, then B belongs to G. If B belongs to G means what? F inverse of B is measurable. F inverse of B is measurable. Okay, understand this? So, the given statement is if B contained in Y is a Borel set, then F inverse of B is a measurable set. Okay, this is one result. So, Lebesgue measure, this is a main part of all these discussions. Say Lebesgue measure. If E is a measurable set, then the Lebesgue measure denoted by m of E. Then the Lebesgue measure denoted by m of E is defined by m of E is equal to m star of E. M star of E means what? Outer measure of E. So, here Lebesgue measure is defined on the measurable sets. Lebesgue measure is defined on the measurable sets. That means M is the set function obtained by restricting our outer measure function M star to the family of only measurable sets. Okay, thus M is the set function obtained by restricting the set function M star to the family say mu of only measurable sets. Okay, this is what's meant by Lebesgue measure. So now we have, look here, another important proposition. If Ek, k is equal to 1 to infinity, is a sequence of measurable sets. If Ek, k is equal to 1 to infinity is a sequence of measurable sets, then measure means Lebesgue measure here. Okay, then measure of union k is equal to 1 to infinity Ek is less than or equal to summation k is equal to 1 to infinity measure of Ek. And if Ek, k is equal to 1 to n is a finite sequence of disjoint measurable sets, then measure of union k is equal to 1 to n Ek is equal to summation k is equal to 1 to n measure of Ek, right? So let us come to the proof. So we know that if Ek is a sequence of measurable sets, then union k is equal to 1 to infinity Ek is also measurable. We have proved these results. And so what you can say, measure of union k is equal to 1 to infinity Ek is equal to what? These are measurable means what? It becomes outer measure of M star of union k is equal to 1 to infinity Ek. Okay, and measure of Ek is same as M star of Ek because each Ek is measurable, right? Therefore, but we know that M star of union k is equal to 1 to infinity Ek is less than or equal to summation k is equal to 1 to infinity M star of Ek, because we have proved outer measure is subadditive, countably subadditive. So we are using this property. Therefore, since union k is equal to 1 to infinity Ek is measurable, so outer measure is same as the Lebesgue measure. So this is M of union k is equal to 1 to infinity Ek is less than or equal to summation k is equal to 1 to infinity M of Ek. Measure of Ek means Lebesgue measure of Ek. And if you come to the finite case, say, look here, if Ek, k is equal to 1 to n is a finite sequence of disjoint measurable sets, then union k is equal to 1 to n Ek is also measurable. This we have proved. And so measure of union k is equal to 1 to infinity k is same as outer measure of union k is equal to 1 to n Ek, and measure of Ek is M star of Ek. But already we have proved for the finite case, outer measure is countably additive, right? Sorry, finitely additive. Outer measure is finitely additive. So this is equal to M star of union k is equal to 1 to n Ek is equal to summation k is equal to 1 to n M star of Ek. This result we have proved. So here this union k is equal to 1 to n and Ek is measurable means for the Lebesgue measure, okay, so it coincides with the outer measure for the measurable sets. So this implies M of union k is equal to 1 to n Ek is equal to summation k is equal to 1 to n M of Ek. Thus we have proved both the conditions. Okay. Take next theorem. Say Lebesgue measure is countably additive. Lebesgue measure is countably additive. That is, if Ek k is equal to 1 to infinity is a countable disjoint collection of measurable sets, then measure of union k is equal to 1 to infinity Ek is equal to summation k is equal to 1 to infinity M of Ek. So Lebesgue measure is countably additive. Yes, proof. If Ek k is equal to 1 to infinity is a collection of disjoint measurable sets, then from the above proposition what will happen? We get M of union k is equal to 1 to infinity Ek is less than or equal to summation k is equal to 1 to infinity M of Ek. Thus we have proved this result. And for the finite case, M of union k is equal to 1 to n Ek is equal to summation k is equal to 1 to n M of Ek. This is 2. Now union k is equal to 1 to n Ek is certainly contained in union k is equal to 1 to infinity Ek. This is always true. Therefore we have M star of union k is equal to 1 to n Ek is less than or equal to M star of union k is equal to 1 to infinity Ek, right? This implies union, since union k is equal to 1 to ek and union k is equal to 1 to infinity ek are measurable. So yeah, outer measure is coincides with the Lebesgue measure. So m of union k is equal to 1 to n ek is less than or equal to m of union k is equal to 1 to infinity ek. K is equal to 1 to infinity ek. This implies, but from 2 the left hand side becomes summation k is equal to 1 to n measure of ek less than or equal to m of union k is equal to 1 to infinity ek. Okay. Now we can see that the RHS of the above inequality is independent of n. Therefore we can raise n to the infinity also. Means for every n this is true. For every n this is true means, so if you take summation k is equal to 1 to infinity measure of ek is less than or equal to union k is equal to 1 to infinity ek. So we call this as number 3. Now first one is, one says measure of union k is equal to 1 to infinity ek is less than or equal to summation k is equal to 1 to infinity measure of ek, and 3 says the reverse. So from 1 and 3 we have m of union k is equal to 1 to infinity k is equal to 1 to infinity ek is same as measure of, so is equal to summation k is equal to 1 to infinity measure of ek, right? Let us take up this definition. A countable collection of sets ek k is equal to 1 to infinity is said to be ascending. You know this is a basic result, is said to be ascending if en is contained in en plus 1 for every n, and is said to be descending if ek plus 1 is contained in ek for each n, or for each k. Here since if k we have taken k for each k, right? So based on this we have one result. So this theorem says if I is equal to 1 to infinity is a ascending collection of measurable sets, then measure of union, measure means Lebesgue measure of union I is equal to 1 to infinity ei is equal to limit n tends to infinity measure of en. Measure of union I is equal to 1 to infinity ei is equal to limit n tends to infinity measure of en is one. Second one, if I is equal to 1 to infinity is a descending collection of measurable sets, and measure of E1 is finite, then measure of intersection I is equal to 1 to infinity ei is equal to limit n tends to infinity measure of en. Okay. So these two are the results. So now here measure of E1 is, assuming that measure of E1 is less than infinity is very important in this case. Okay. So you just collect the proof from any of the textbooks, and so you write this in your assignments. Okay. So next proposition, if E1 and E2 are measurable sets, then measure of E1 union E2 plus measure of E1 intersection E2 is equal to measure of E1 plus measure of E2. Okay. So now if measure of E1 or E2 is of infinite measure, then the proof is trivial, because it will be, say, if E1 or E2 is infinity, then it will be infinity. Both the cases, in both sides we will have infinity, and the proof will be very trivial. So let measure of E1 is finite as well as measure of E2 is to be finite. Now you observe that E1 union E2 minus E1 intersection E2 can be written as E1 union E2 minus this one can be written as E2 intersection E1 intersection E2 complement, right? So this is equal to E1 union, this is E2 intersection, this can be written as E1 complement union E2 complement. So this is equal to E1 union E2 intersection E1 complement, E2 intersection E1 complement union E2 intersection E2 complement. E2 intersection E2 complement becomes empty, right? So this is equal to E1 union E2 1 intersection E1 union E1 complement. Okay, E1 union E1 complement is the whole set. So if we take intersection of that with E1 union E2 means if we get E1 union E2 only. So you call this by number 1. So this set will be equal to E1 union E2. Now we can see that this set E1 as well as E2 minus E1 intersection E2 are disjoint sets. These two are disjoint sets because if you assume that some x lies in this intersection, some element lies in this, say you assume that x lies in E1 intersection E2 minus E1 intersection E2, then what will happen? X belongs to E1 as well as x belongs to E2 minus E1 intersection E2. Now x belongs to E2 minus E1 intersection E2 implies x belongs to E2 and x doesn't belongs to E1 intersection E2. This implies x belongs to E2 and x doesn't belongs to E1 and x doesn't belongs to E1 intersection E2 means what? X doesn't belongs to E1. Okay, x doesn't belongs to E1 because as x doesn't belongs to x belongs to E2 means, right? So x doesn't belongs to E1 intersection E2 means x may is in E1 or x may is in E2. But x belongs to E2 means it cannot lies in E1. So I assume that x doesn't lies in E1. This implies x belongs to E2 and x doesn't belongs to E1, which is a contradiction because already we have got like x belongs to E1. X belongs to E1. So these two sets E1 as well as E2 minus E1 intersection E2 are disjoint sets. Disjoint sets means what will happen? So if we apply the measure on both sides, so you can apply the measure, say measure of E1 plus measure of E2 minus E1 intersection E2 is equal to what are the right hand side? Measure of E1 union E2. So this is measure of E1 plus this is applying this one. So measure of E2 minus measure of E1 intersection E2 is equal to measure of E1 union E2, right? So this is equal to measure of E1 plus measure of E2. You transform this term to right hand side, you get measure of E1 union E2 plus measure of E1 intersection E2. That is the required results. These are the 3 results for this class. Okay, I'll continue in the next class.